If you've taken an introductory course in calculus, you might have come across the mean value theorem, which states that if f is continuous on a closed interval a to b and differentiable on the open interval a to b, then there is some c in between a and b such that f of b minus f of a is f primed of c times b minus a. Let's take a moment to appreciate what that is saying. If we draw a graph of our function, let's just say it's curving up like this, and we pick some points A and B. Now let's connect the line that goes through the points A and B. That gives us a nice secant for our graph. And the slope of that secant is f of b minus f of a over b minus a. That's just the rise over run. And now you might notice that the derivative is the slope of a tangent. So if these are equal, then there must be some point C in between a and b where the slope of the tangent is f prime of c, which equals this f of b minus f of a over b minus a. So the mean value theorem equates a slope of a secant with a slope of a tangent and seems a little bit abstract. And why is this useful? I want to talk about three different theoretical applications for this and how it might power stuff that you've been using this whole time without seeing a proof of it. Okay, so the first application I want to talk about is to increasing and decreasing functions. So just as a reminder, we say a function is increasing on the closed interval from a to b if taking x less than or equal to y implies that f of x is less than or equal to f of y. So in other words, if my input increases, then my function increases. So I get a larger input, I get a larger function value. And of course, we can say the same definition for decreasing by just switching this inequality around. So in other words, if x is less than or equal to y, then now f of x should be greater than or equal to f of y. Or in other words, if I have a larger input, then my function value gets smaller or larger in the negative direction. Okay, so you might have learned from your calculus class that we can check for increasingness with the derivative. I'm going to record this as a proposition. So this proposition is that if f is continuous on the closed interval a to b and differentiable on the open interval a to b, and its derivative is always positive or zero, or always non-negative on this interval a to b, then f is an increasing function. F is increasing on this interval. So in other words, instead of checking this annoying definition, we can just check for the sign of the derivative. If it's non-negative, then that means it's increasing. But why is this true? This is not easy to prove. You might have seen a justification for this coming in the form of a picture. So for example, if we know that the derivative is positive, then it's behaving like its tangent line, and a positive slope means it's going up, so the function should be increasing. But if you try to sit down and prove this rigorously, it's not trivial. But luckily, our friend, the mean value theorem, comes to help us here. So let's see a proof of this. Let f be continuous on the closed interval a to b and differentiable on the open interval a to b with the derivative of f being non-negative, so greater than or equal to 0 for every x in a to b. Now let's pick two arbitrary points, x, and I'm going to pick it to be strictly less than y in the closed interval a to b. Because if they're equal, then there's nothing really to prove here. So by the mean value theorem, there is some c in between x and y such that f of y minus f of x is equal to f primed of c times y minus x. Okay, but we said that the derivatives are always non-negative, so f prime of c is greater than or equal to 0, and y minus x is strictly larger than 0 because x is strictly less than y. So in other words, f of y minus f of x has to be greater than or equal to 0. But just by rearranging, that implies that f of x is less than or equal to f of y. So since x and y were arbitrary, we see that f is increasing. And of course, the same results can be said about the decreasingness. So if our derivative is non-positive, then it's decreasing. And you can argue the same logic. Okay, so now we have this result about the increasingness of our function on a more rigorous standing. So the second result I want to talk about is antiderivatives. So when anti-differentiating, we always seem to add a plus c at the end. For example, if I take an indefinite integral of x dx, I might write that as x squared over 2 plus c. So my question is, where does this plus c come from? Why is there a plus c hanging around? And how do we know that this is true? How do we know that there's not some obscure function that has the same derivative as x squared over 2 plus c that we aren't writing down? So I'm going to write this as if two functions have the same derivative on the open interval a to b, then they differ by a constant. So this is a very nice result that says that there is no weird functions that can show up. It's only one function and I can shift it around by a constant. And we're going to prove this by first proving a simpler case. And of course, our friend the mean value theorem is going to help. So what's the simpler case? I'm going to write it as a proposition. If f primed of x is equal to 0 on the open interval a to b, then f is constant on the open interval a to b. Now, the converse of this is very simple. Of course, if f is constant on a to b, then its derivative is 0. But the direction I'm trying to prove here is a bit more nuanced. I'm saying if the derivative is 0, then it must be constant. Again, I would encourage you to try to think about how to prove this. It's not immediately obvious from the basic tools that you have. But again, our mean value theorem will help us. So let's see if we can prove this. Again, I want to fix x less than y in a to b, arbitrary. Then the mean value theorem says that there is some c in between x and y, such that f of y minus f of x is f primed of c times y minus x. So same setup that we've seen a couple times already. But f primed of c is 0, is what we're assuming. So that cancels out the whole right side of that equation, and we're just left with f of y minus f of x equals 0, or f of x equals f of y. But that's true for any x and y in a to b. So that implies that f of x is constant on a to b. So this is proving this nice fact that only antiderivatives of 0 on a to b are the constant functions. And we can upgrade this to our general result very simply. So let's see a proof of the theorem now. Suppose that for all x in a to b, we have that f primed of x is equal to g primed of x. Now I'm going to let this function h of x be f of x minus g of x on the interval a to b, and we're going to show that h is a constant function. So notice that h primed of x is just f primed of x minus g primed of x, just by definition. So that's equal to 0 because we're assuming that f primed of x is equal to g primed of x. And that's true for all x in a to b. So in other words, by our proposition, h must have been a constant. So f of x minus g of x is a constant, and therefore f of x is equal to g of x plus c. So now this gives us a rigorous background to anti-differentiating functions. So if I know one antiderivative of a function, then I know all antiderivatives of that function by just adding constants. And that's where all these plus c's come from when doing anti derivatives or indefinite integrals, same thing. Okay, so the last result that I want to talk about here is talking about roots of polynomials. So this is a more of a cute application, but we can prove a weaker version of the fundamental theorem of algebra by use of Rolle's theorem or the mean value theorem. So in particular, what I want to prove is that if f is a polynomial of degree n, and I'm going to specify that it's greater than or equal to 1, then it has at most n roots, distinct roots. Okay, so let's see if we can prove this. I'm going to prove this inductively. In other words, I'm going to build up the degree from lower degrees. So let's start with a degree 1 polynomial, a linear function. So if f of x equals ax plus b, where a is not 0, then f of x equals 0 precisely when x equals negative b over a. So this is a unique root for f. It's degree 1. So base case holds. Now I'm going to suppose that f of x is a degree n polynomial, and that any polynomial of degree n minus 1 has at most n minus 1 distinct roots. Now notice that the derivative of f is a polynomial of degree n minus 1 by the power rule. Let's suppose for contradiction that f had n plus 1 or more distinct roots, and let's order them. So a1 is less than a2 is less than all the way up to an is less than an plus 1. So each of these are roots for f. Now I'm going to apply the mean value theorem or Rolle's theorem to each interval ai to ai plus 1. And we see that there must be some xi in ai to ai plus 1 such that f of ai plus 1 minus f of ai is equal to f primed of xi times ai plus 1 minus ai. So mean value theorem set up. But of course, since the AIs are just roots of f, the left-hand side is just 0. And I know that AI plus 1 and AI are distinct, so AI plus 1 minus AI is strictly greater than 0. It's not 0, which implies that f primed of xi must be 0. but there's one of these for each interval, and there's n intervals. So this tells us that there are n distinct roots for the derivative, but this is a contradiction because we said that f prime is a degree n minus 1 polynomial, and that has at most n minus 1 distinct roots. Okay, so that's a nice little showcase of some of the power of the mean value theorem. And it's a lot nicer and deeper than maybe it looks at first glance. And maybe you don't get into that in the first calculus course, depending on what level you're taking it at. But it shows how the mean value theorem actually powers several of the main properties of functions that you use in calculus. And it does so by acting as a sort of bridge between a function and its derivative.